So I'm going to spend a little bit of time telling everybody today about some exciting things that we've been doing, quantum Monte Carlo calculations, thanks to Blue Waters. So this is a team effort. This is part of a PRAC called Breakthrough Petascale Quantum Monte Carlo Calculations. Our PI, Shiwei Zhang, isn't able to be here today, so I'm Elif, lower line here. I'll be giving the presentation. And David Sepperly and Lucas Wagner, who is also here, are also part of this team. So I thought I would start with just a quick question. What do the following things have in common? And what I'm showing are here, these are solar cells, photovoltaics being installed. This is actually last week on the roof of the White House. This is Jupiter. This is the inside of a geode with diamond. And then underneath that, we have a superconductor. Well, and this is the answer that I'm getting at. The idea here is that all of these things, their materials can be described by the solution of an interacting quantum mechanical differential equation, a differential equation. And so I've summarized here what that differential equation looks like. It's, in many ways, we can reduce it to an eigenvalue problem. The only good thing it has going for it is that it's linear, but apart from that, things become very complicated. And here's why. Here are the different terms that appear in that differential equation that we are worried about solving. The first term, kinetic energy of electrons. Think about that term as the term that makes electrons want to spread apart. And then all the other terms are potential energy terms. Coulomb interactions between electrons, negatively charged, and nuclei, positively charged. So that's a pooling together term. Nucleus-nucleus interactions. And if it just stopped there, we would be okay. If everything stopped there, then the solution to this equation, we could write it in a separable form, and the problem would be more or less solved. The problem is that last term that I'm showing there, the electron-electron interaction, and that's what makes this equation a difficult one to solve. It's a many-body interacting system, and the more electrons you have, the more those interactions grow very quickly. So if you think about how many electrons we have, 10 to the 23rd per cubic centimeter of materials, you see this problem quickly gets out of hand. So finding a good way to actually trying to solve this problem has been historically a challenge that we've been working on and making some pretty good improvements. What I'm going to tell you about today is how Blue Waters allows us to do some things of pretty unprecedented accuracy as far as solving the Schrodinger equation goes. So, quick history of our problem, just to put in perspective what it is that we're doing. Many different approaches have been used historically, so we're going back now 100 years or so in history, to try to figure out ways to approximate the solutions to this problem. So Sommerfeld model, well, that's the easiest thing. Just forget about the interactions altogether. Don't worry about them and see what you get. First thing to try, of course. Then there are Hartree and Hartree-Fock methods. At that point, what we're doing is we take that many-body interacting part of our equation, and we simply, instead of explicitly considering all the electron interactions one at a time, we consider the electron interaction in an effective or average way. A given electron sees all the other electrons as a mean field or on average. Density functional theory, so this is the workhorse method of the computational materials community now. In this case, we're using, it's also an effective mean field approach to dealing with these interactions. Some chemistry methods, coupled cluster, quantum chemistry. We worry about these interactions by trying to expand the basis set for the wave function in these single particle determinants. And then there's what I'm going to talk about today, quantum Monte Carlo methods, which you can just think about as biting the bullet. It is a statistical approach. Rather than approximating the problem, we're going to try to solve the real problem, including all of those interactions explicitly. So why quantum Monte Carlo? This is just a summary chart that compares quantum Monte Carlo methods to some other techniques that are used in this community. The first one I'm showing, density functional theory, I'll talk a little bit about. And then the next two are various tweaks to density functional theory. That's a pretty good approach, actually. It does well most of the time, but I'll show you today some instances where that conventional approach doesn't seem to be quite good enough. GW methods, also another kind of perturbation theory-based approach, and then QMC, quantum Monte Carlo methods. Here's what I like about QMC is that amongst all of these techniques, it is one that it is the one technique where you are directly trying to solve the many-body interacting Schrodinger equation. And so what that means, you are biting the bullet, but at the end of the day, we know that if we do a better job of applying the technique, we will get the right answer. And that's different from any of the other approximate methods that we use. So that's nice. That means I get accurate total energies, I get accurate band gaps, for example, and the scaling is not that bad, cubic with the number of electrons in the system. Here's the performance of one of our QMC codes, QWalk, on blue waters. And what you see is we've actually been able to demonstrate pretty good scaling up to several tens of thousands of cores. Actually, I think we've done a little bit better than this now. I think there's an updated version as well. So what we're able to do is make use of a lot of the blue water system to be able to apply the quantum Monte Carlo technique now. Thanks to all the availability of these cores, we can apply it to large, ambitious problems that we wouldn't have been able to go after previously. So here's our team. So like I said, our goal is quantitatively simulating these interacting many-body systems. Shiwei Zhang, our PI, his area is focusing on new methods, so development of methodologies for quantum Monte Carlo methods. David Sepperly in the physics department here focus on materials at extreme pressures, so what might the interior of Jupiter look like? What happens to hydrogen when you subject it to lots of high pressure? Lucas Wagner, interested in correlated electron systems, transition metals, superconductors, other sort of schemes. And me, I am the one engineer out of the otherwise team of physicists. I'm interested in, and I think this is in some sense maybe a demonstration of progress, is that we're taking a tool of the physics community and bringing it into the engineering realm. We're now trying to apply it to real materials, to understanding the properties of real materials as well. So just to give you a little bit of a sense of what we are doing when we use quantum Monte Carlo calculations, I first spent a little bit of time talking about comparison of quantum Monte Carlo to traditional density functional theory, which is the most commonly used approach for trying to solve these electron problems. Density functional theory, the idea here is that we take those interactions between all those electrons and we try to describe them in an effective or a mean field way. And that's what this diagram here illustrates. The real system, lots of electrons. Our approximate system, one electron that sees all the other electrons in an average kind of way. This is actually been a very successful technique in many ways. This is Walter Kohn receiving the Nobel Prize in Chemistry for the development of some of the ideas behind the technique. And this is the approach that I would say is more or less the workhorse of the computational materials modeling community. And by contrast, in quantum Monte Carlo methods, like I said, this is biting the bullet. We're using statistical or Monte Carlo approaches to actually solving the many-body interacting Schrodinger equation. So we take all those interactions into account here. Here's a quick cartoonish figure of what that might actually look like. This is one flavor of quantum Monte Carlo called diffusion Monte Carlo. And what I'm showing here is, in this approach, well, if you stare really hard at the Schrodinger equation, it looks a little bit like a diffusion equation. And so in diffusion Monte Carlo, what we actually are doing is we take a guess at what that wave function looks like. And then we statistically, we describe that wave function by this distribution of walkers in that 3 times n dimensional phase space, n is the number of electrons in your system. And then we propagate them. We move them around according to the dynamics of that diffusion equation. And those walkers will, as in this case, over time, they'll move to areas where the potential is low, they'll move out of areas where the potential is high, and you'll eventually converge to a stationary state. So that's how quantum Monte Carlo works. And if DFT is the workhorse technique, I would call this one a bulldozer. So it is an approach that is going to get the job done for you, and you know you're going to get good results. Okay, so What I want to do now is show a little bit of examples of the types of things that we're working on using quantum Monte Carlo methods on blue waters, types of things that would be very hard to do without a system that gives us access to as much cores as we get on blue waters. Here's our first example. This is work that Lucas Wagner has been carrying out, looking at a material called vanadium dioxide. Let me tell you a little bit about this material. It's actually a really fascinating, VO2 is the chemical formula. It's a fascinating material. The reason is it's a material that undergoes a room temperature phase transition from an insulating to a metallic state. High temperature, metallic, low temperature, insulating. The reason for that phase transition has been debated for quite a while in the physics community. Just as an example of just the richness of the physics inside the Schrödinger equation, it's kind of an amazing material system. When that phase transition occurs around 340 degrees Kelvin, the change to the lattice structure in vanadium dioxide is barely perceptible, a small 1% change. What happens is the lattice contracts by a little bit in one phase, in the high temperature phase, which I'm calling rutile over here. You can think about those vanadium atoms as being uniformly distributed along a line. If I cool it down, take it through the phase transition to the monoclinic phase, rather than uniformly distributed vanadium atoms, those atoms dimerize. So they couple together in pairs of two. And so that's what we're showing here on this diagram, is that dimerization taking place. I've exaggerated on this diagram the degree of that dimerization. It's actually really small, but you make a small change like that, and all of a sudden the electrical conductivity of the material changes by about 4 orders of magnitude. So it's an impressive demonstration of what's hidden inside of the Schrödinger equation itself. So if you go back to this, like I said, this is a problem that has quite a history. 1970s, model was thrown out to try to explain why this phase transition occurs. It was put out by John Goodenough. And his theory about this model was that 2 things take place. Number one, as we cool the temperature down from the metallic system to the insulating system, we get that dimerization, a Peierls instability. That structural transition is driven by the Peierls instability. We also get, due to electron correlation effects, electrons trying to avoid each other, they're all negatively charged and want to stay away from each other, system turns into an insulator. Now, for a very long time, big debate about which of these 2 drives the actual phase transition. Is it an electron correlation-driven transition, or is it a structural phase transition? What we've been able to do using quantum Monte Carlo techniques is play with this system, model both of the structures and all of the different possible spin states, and show that if we don't include the spins, we get the structural transition, but no metal insulator transition. If we don't include the structure, there is a possible low temperature ferromagnetic ordering, but there's no metal insulator transition. In other words, it's not really a question of which one drives the phase transition. The metal insulator transition itself is a cooperative transition. You need both. And what that comes down to at the end is that the Goodenough model turns out was good enough. Almost, because Goodenough didn't have the spins in there entirely. So that's one of the nice things we've been able to do. Here's another example. We've been able to explore some very complicated material systems, high temperature superconductors, using quantum Monte Carlo methods. Now, high temperature superconductivity is something that we don't have a very good explanation for. We understand low temperature superconductivity to some extent. We understand that pretty well, phonon electron coupling. That phonon-electron coupling that causes low-temperature superconductivity isn't enough to give us high-temperature superconductivity. Some indications that magnetism plays a large role in describing high-temperature superconductors. So what we've been able to do using quantum Monte Carlo methods on blue waters are actually take some of our cuprate materials, our high-temperature superconductors, and calculate their properties using quantum Monte Carlo methods. And so the diagrams that I'm showing here calculated values of J, which is the energy cost of flipping the magnetic spins on the electrons, the total magnetic moment on the copper atoms, the band gap of the material itself, and the last thing, the buckling frequency. So this is the frequency of the lattice vibrational mode associated with this D wave buckling mode related to the superconductivity. And for these different parameters, this black line is the experimental value. The red dots are our previous degree of accuracy coming from different techniques, so more conventional approaches. And what I'm showing in blue, these are the calculated values using quantum Monte Carlo methods. What else? So we've been able to apply quantum Monte Carlo methods to real materials as well. Here's an example. Something that I'm interested in quite a bit is describing the properties of defects in semiconductors. We picked a challenging problem to begin with. The problem is looking at zinc oxide. So zinc oxide is a semiconductor that notoriously has been very problematic from the modeling perspective. So this is the experimental band gap of the material, 3.4 electron volts. What that is the energy cost, the energy necessary to take that highest level electron and promote it to the next available state. 3.4 eV in reality. The problem is that in our conventional methods, that gap is pretty grossly underestimated, so about 0.75 electron volts or so. So now if you think about putting a defect inside of zinc oxide, maybe nitrogen was the one that we were concerned with, that defect introduces a level somewhere inside that gap in the real world. But if my calculated gap is only 0.75 eV, there's no way I'm going to be able to get that right. The nice thing is that with quantum Monte Carlo methods, you calculate the gap, you do get it right, and actually our calculated energy level for nitrogen defects in the material agree quantitatively with the most recent experimental results. Here's one more. We've been trying to apply quantum Monte Carlo methods to photovoltaic materials of current research interest. The material that I'm showing here is a relatively newcomer material. It's a CZTS, copper, zinc, tin, and sulfur or selenium. If you look at the microstructure of this material, you'll see why it's so impressive. What I'm showing you there is not a beautiful microstructure in many ways. So grain boundaries all over the place, voids, other sorts of things. And despite that, this is an 11% efficiency solar cell material right here. If silicon, for example, our conventional photovoltaic material, if the microstructure looked like that, you could forget getting a photo response out of it. So what's amazing about this material is that despite the presence of defects, voids, and grain boundaries, it does a pretty good job. Now, the history of this material is interesting. It's one where initially we were able to make very quick progress in increasing the conversion efficiency up to 11%. We got there very quickly. Since then, we've kind of saturated or petered out, and now we're trying to understand why. Most likely suspect is some defect that is forming in this material that is suppressing the photovoltaic response of the material itself. Something that's very hard to assess using experimental techniques. Something that's been very hard to assess historically using computational methods as well, because this is another situation where our conventional methods don't quite get it right. I was telling you about the band gap problem earlier. This is one where if I use a conventional approach, DFT predicts this is more of a metal than a semiconductor. So we have to go to high accuracy techniques. QMC happens to, what I'm showing on the diagram here on the left-hand side, get the band gap right, both for CZTS and CZTSE. And so we've moved on now to trying to calculate formation energies of defects that might be responsible for reducing the photo response of the material itself. Okay, so I'll spend just a minute talking about a little bit of work on methodology development that Shiwei Zhang is carrying out. One of the kind of historic landmark problems in computational interacting electron physics seems like it should be very simple, right? Take a chromium dimer and dissociate it and see how the energy varies as a function of separation. Turns out that has become a benchmark test for the accuracy of a lot of our techniques and methods. And so what I'm showing here are several the experimental variation of the energy versus at the nucleus separation for several different techniques. So coupled cluster, usually considered to be a benchmark approach, you see, isn't able to capture the physics quite right. Quantum Monte Carlo techniques, particularly a technique that Shiwei is developing, auxiliary field QMC, is doing a pretty good job of finally capturing all of the interactions properly as we dissociate that chromium dimer. And lastly, that auxiliary field approach, where we're really trying to accurately, actually even move past conventional QMC accuracy, get a little bit further. We're able to calculate band structures for materials like diamond and zinc oxide once again. And our preliminary work is showing that we're getting very good agreement with experiment on a lot of this. Okay, so quick conclusion. Main idea is that the access to the blue water system has really has enabled us to choose some pretty ambitious problems that we otherwise wouldn't have been able to do in many body interacting electron physics. We have a lot of ideas for where to go next with this. I listed them here, and that's it.